Today we're going to talk more about a function's graph. The first objective asks us to determine whether a function has intervals that are increasing, decreasing, or constant. Now we will write these intervals with what is called interval notation. And when we write the answer in interval notation, we will always be going from left to right. That is how you read a graph. Now, intervals are also always written in terms of the x value. So let me explain. I'll start over here on the left-hand side, and I will start tracing my graph. Notice that the first portion of the graph looks horizontal or straight across. That is called constant. So we say that this graph is constant on the intervals from negative infinity to -3. Now always use parentheses just like an ordered pair when you're doing interval notation for increasing, decreasing, and constant. Also notice the reason I use negative infinity is because this graph just shows a portion of the picture. It would continue out to the left infinitely. And when it stops being horizontal or flat and constant, notice that it stopped at the x value of -3. So it's the x value that I always look for. Now, let's continue tracing the graph. We've already done the left-hand part. The next part of this graph goes like this. Notice that it's going downward. Downward would mean decreasing. So this function does indeed have a section, an interval, that is decreasing. I'll put it in interval notation. It decreases from the x value of -3 to the x value right here, and I notice that is a -2. So I will write -3, -2. Again, those are the x values that correspond to the points on that interval. Now if I continue tracing from left to right, I have this big long section of the graph that goes uphill. Uphill would be increasing. And this one would be increasing from the -2 where it began, right down here. And it increases up to this point, right up here. Now that point, notice, goes to the +2 on the x-axis. Always use the x values. And then I'm almost done. If I continue tracing this graph on out to the right, it gets flat again. Remember, flat would be constant. So I'm going to go up here and put a second interval for the constant. The constant would start at the +2, and then it goes all the way out to the right. When it goes out to the right, I call that infinity. This sideways 8 looking symbol stands for infinity, and notice I use negative infinity over here on the left to stand for the graph going all the way to the left. The shape of a graph can also be classified by its symmetry. Any of you who have to take art will probably study symmetry. We have even and odd symmetry, and then of course some things are not symmetrical at all. First off, let's recall what the value for even and odd would be. If you have numbers with like 2, 4, 6, 8, these are called, of course, your even numbers. 1, 3, 5, 7 are your odd numbers. So even symmetry is symmetry about the y-axis. So it's going to be what we call symmetry that is side by side. You may be the type person who hangs photographs in your room that are side by side. Okay, odd symmetry is symmetry about the origin of the graph, and it actually looks diagonal. I tend to be an odd symmetry person. Whenever I hang a photo, I like to hang something, you know, over here on the left and then down here towards the right. So, you know, I'm just odd like that. Okay, now, how can you tell if a function is even, odd, or neither? Well, first off, if you have, we're going to look at polynomial functions. If a polynomial function has only even exponents, remember even numbers are like 2, 4, 6, 8. If it has only an even exponent, then you can be assured that the symmetry is even. If you recall from graphing, x squared is a parabola, and plus 6 would be the y-intercept, so that graph, that shape is side by side. Now, jump over to example C. Example C over here has both an even and an odd exponent. If you have both even and odds mixed up in the same problem, then we say that has no symmetry. That would be neither. Now in the middle here, you can probably guess what that one's going to be. It has a 3, which is an odd number, and then it has just x. That's an understood 1. Both of those exponents are odd. So we say that that does have odd symmetry. The only time when this does not hold true is if you have an odd function, g of x equals x to the third, and then you have a constant with it, then that is a neither. That's kind of just an exception to the rule. So if you have one like that with a constant number like that plus 3. Now in addition to using the exponents, you can also simply look at graphs. This first graph, notice how it is perfectly symmetrical side by side. The left and the right sides look like mirror images of each other across the y-axis. This is symmetry about the y-axis, which is even. Now, with our second example here of a graph in example E, notice it almost looks even. It looks like that shape of a W, but do you see how it's off-centered at the bottom? One point is over here at -1, 0, and one's at 2, 0. That makes it a little bit off. So if it's off-centered like that, we would say it has no symmetry. That would be neither. Then this last one is the S-curve that we had talked about previously when we were graphing. This has a diagonal symmetry to it through the origin. It passes through the origin, and notice part of it's in quadrant 1 and part of it's in quadrant 3. Those two quadrants are diagonal to each other. So we say that that is odd symmetry.